with the contributions. Okay. And then I will follow to the Flipper methodology, to Motif Method, Primus Architecture, and IoT Reward Method. The methods, architecture, and the methodology, they assist to validate my hypothesis. And finally, the conclusions and the learned lessons and future works. So my thesis contest is in the Internet of Things because we have a huge amount of device connected to the IoT, and we have different type of device connecting data from different environments. These different devices and huge amount of device, they generate a huge amount of data. So we have a scenario with different devices and with a lot of data. And into IoT, we have the smart healthcare market that is an important scenario into the IoT that represent a big and important scenario collecting data from the user health. Talking about IoT, it's important to mention the global home healthcare that is composed by a smart home with different devices collecting data from the smart home and the environment. And also we have devices collecting data from the user health, like a body temperature sensor, like a blood pressure sensor, a sleep monitor, and many others. So this thesis concentrates the efforts in the smart home with different type of devices collecting data from the environment and from the user health. So in IoT, we have a lot of data and different type of data being collected every day. If we look to this data and use them to make smart data-driven decisions, we can get valuable insights, improve outcomes, optimize operations, prediction of trends, and also actionable insights. So this data can help us in the network performance requirements, so to achieve the requirement of smart applications from IoT. And these valuable insights from the IoT data can assist on the development of tailored defense mechanisms. So having said that, we are talking about a large-scale network of the IoT that has a massive amount of data. This data is generated from different applications, and each application or device requires different requirements. And we're also talking about sensitive data because in the smart home, we have private and critical data from the users. And all this data collected from the IoT is unstructured. So the thesis has threefold concerns regarding performance, and in specific, the smart application requirements, like the smart healthcare requirements, like low latency and high reliability. And also we are worried about the security and privacy because there are the network traffic-based attacks that can explore the smart healthcare network traffic to violate the user's privacy. So in this scenario, we have sensitive data and we need to research about privacy and security in the IoT. So talking a little bit about the performance, we are worried about the critical applications. And when we are talking about critical applications in IoT, we are talking about smart healthcare. Smart healthcare has different devices and applications generating different type of data. And each application demands different requirements. For instance, telemedicine demand high throughput, and emergency response demands high reliability. When we researched about the requirements and the most critical, we can see the low latency and high reliability in several applications from the smart healthcare. Because of that, we concern with this type of requirements from the smart healthcare applications. Also, smart healthcare applications and the smart home, they have sensitive data and private data. But in a smart home, we can have attackers that are performing traffic-based side channel attacks to infer the user activities and the user routine, just looking and analyzing the network traffic data. So we are worried about the security and privacy of this data from a smart home. So how to improve the performance, security, and privacy from the IoT? when we look to the data, we just saw unstructured and uncorrelated data, because this data collected from the sensors and from the device, they don't have a particular type or format. So to get valuable insights, it's necessary to perform an activity or to structure this data. Having said this, the hypothesis of this thesis is the IoT network data instrumentation and feature exploration to support the security and performance management in order to achieve the improvement of performance of smart healthcare applications, to improve the security from a smart home and the privacy of the users from this smart home. So if we look to this data and perform a network data instrumentation, this can support these network actions. Based on this thesis, we have the main research questions that guide our research. And the main questions, they are related to the performance, security, and privacy. So regarding the performance, the main question is it possible to create a broader methodology for network data instrumentation to support different purposes? And these purposes are about network and security management. So if we instrument network data efficiently and apply some intelligence, is it possible to know what application devices generating traffic? And based on this information, this can assist the achievement of smart healthcare applications. So the network data instrumentation can assist the performance. And at the same time, the network data instrumentation can assist the performance management. Adversaries also can use this information to violate users' privacy and security. So is it possible? And network data instrumentation can also assist the tailored development of network security mechanisms. So we can use this data, the network data instrumentation, and the valuable insights from this network data instrumentation to assist the security and performance. Having said that, the main goal of this thesis is the IoT network data instrumentation through network data analysis and feature exploration to support other network actions like the security and performance management. To do this, we propose the Flipper methodology. The Flipper methodology performs a network data instrumentation on the network traffic capture from a smart home. And this network data instrumentation get valuable insights to support and assist other network actions. So this supportment, they assist the Motif Method. We proposed Motif Method to identify the traffic of smart healthcare applications. And this knowledge of this application, it assists the Primus architecture. We proposed the Primus architecture to achieve the smart healthcare applications like low latency. And finally, we also proposed the IoT reward method that improve the user's home privacy and security based on the network data instrumentation from Flipper. So these are our main contribution from this thesis. So now we can go talk about the Flipper methodology. But first, it's important to make the question, what is network data instrumentation? This is a broader concept from big data analysis, so generally is used for big data analysis and for big data tools like MapReduce. And the network data instrumentation explore, structure, and organize the data to format the data in a structure that we can look and get insights from this data, like in a table or many others type. Generally, the IoT data is unstructured because they do not follow a predefined format. So it's necessary to clean, preprocess, extract, and also it's important to explore these features. This exploration can be made through factor analysis and principal component analysis. Both analyses, generally, they are used as feature selection or feature extraction algorithms, but they also can be used to understand the most representative features from that data. So it's important to understand these data to improve the classification performance or to improve the data analysis and the exploration. But although we follow a network data instrumentation from the literature and from other contexts, at some time the data analysis and exploration funnel tailored to the context. What I want to say with this, there are features relevant specific to each context. When we are talking about medical context, we need to analyze physiological data. And when we are talking about network traffic classification, it's important to understand the network traffic features like the packet size. So if we follow a specific methodology for IoT that instruments the data, we can assist the decision-making, and this decision-making can assist the development of adaptive network solution. This adaptive network solution can assist the network performance management and also the network security management. So we researched in the literature about network data instrumentation, and we found works using for big data analysis to apply big data tools and analyze the data, but it's not in the network context. We found some pre-processing steps to apply machine learning models and identify something, but they did not use the data instrumentation to understand the most relevant features and use these features. And we also found works in the traffic identification field to identify the traffic from devices, applications, and many other solutions, but they did not assist the adaptive network solution. So the analysis of network data and to get the most relevant data is not performed. So we found a gap in the literature and we proposed the flipper methodology for the IoT context. We have the network traffic as input, and first it's necessary to understand the context because the feature extracted and the cleaning, the removing will be based on the scenarios. So it's important to understand if we are in a smart hospital, in a smart home, or many other scenarios. So we can understand the context and the type of features that will be used, cleaning and removing the unnecessary data, extract the features relevant to the context, following the packet level or the flow level. The packet level refers to analyze each packet collected from the network traffic, and the flow level consists of extract the packets belongs to the 5 tuple that refers to the same IP address, the same number of ports from destination and source, and the same transport layer protocol. It's also important to deal with missing data and outliers, so we can replace the missing data with some statistic features. So it's also important to compute the statistic features like the average, mean, max, variance, standard deviation, and many others, because they increase the samples from the data set. And then we can discover the most relevant features applying PCA or FA. So we can understand the features, extract these features, and understand which feature contributes more to represent this data. And we can do this analyzing the features, the behaviors, and the patterns from each features on the representation. And finally, we create a set, a file containing the most relevant features. And here we have an example of this output file that can support the other network actions. So we have the device name, number of packets, mean number of packets, and the day capture. This is an example, and we suppose that these are important features discovered in the flipper methodology. So we can say that flipper methodology is a preliminary step for several purposes. Is the starting point for creating adaptive network solutions for performance and security management. So the flippers serve as support for Motif, Primus, and IoT Regard. So now we can talk about the Motif method that the goal is to identify the traffic from smart healthcare application. And the goal is because the performance management and security management requires network traffic analysis and monitoring to make a smart data-driven decision. So to do this, it's important to understand from where the traffic is coming. So identify the application or the device that is generating that traffic and explore these features. So to do that, we research in the literature about works that try to identify the traffic from smart healthcare applications. And we found 4 main approaches. The first one is the port-based approach that analyzes the number of the port in the network traffic, but has a low accuracy because usual applications hide his traffic behind well-known number of ports. The payload-based that analyzes the payload, the content of the network packet, so it performs deep packet inspections and signature and regular expression, but this approach violates user privacy and we cannot accept this in the smart home. We have the behavior-based approach that analyzes all the traffic that arrives in a host to understand the behavior of that application, but this takes time because it's necessary a huge amount of data. And finally, we found the statistic-based that analyzes side channel data, or network traffic features is the same term. So they applied machine learning models like supervised and unsupervised to identify the traffic from smart healthcare applications. To identify applications, the literature indicates to use supervised approaches. We found two works in the literature applying machine learning for smart healthcare, but they did not present results specific for smart healthcare applications. So based on this, we proposed the Motif method that instantiates some steps from the flipper, but not all the steps. So start capturing the network data through sniffers and preprocess this network data, extracting the MAC address as the ground truth information. Then we preprocess this data for each device according to the MAC address. And this serves as input for the feature extraction phase, where we have the data from each device to extract these features following the packet and flow level. We considered both levels because it was important to analyze both levels. And we also extracted the statistical features from the network traffic. So we have the set of network features plus the set of statistical properties of each device. This serves as input for the fingerprinting phase, where we applied machine learning models to classify the smart healthcare traffic. We evaluated Motif in the trace-based approach. So here we have a picture from the data set, and we have 20 pickups specific for 20 days of capture of collected. And the main goal of this analysis is to identify the traffic from the health-related devices, specifically from the blip care, because it generated just traffic from 3 days, over 3 days. So it's a tiny amount of network data traffic. Here we have the evaluation scenario. So we considered the packet and flow scenario, considering different features from the network traffic, and we created samples with size 3 because blip care generate a small amount of traffic. We considered some machine learning algorithms developed in Python, and we also considered the holdout and cross-validation because the holdout split the data in training, testing, validation, and the cross-validation is split 9 times with device 9 because we have 9 devices, the data set, and is indicated for unbalanced data. And these are the performance metrics. So here we have the mainly results from the Motif method. So here we are talking about the cross-validation method that achieved a good result for the bagging classifier. The bagging is based on the decision tree classifier. So we achieved 98% of accuracy and 87% of recall, but we also considered the classification time, and we have 69 seconds in the flow scenario, and in the packet scenario, we have 214 seconds. So this is a lot for the classification time, but the performance is good from the classifier. And random forest also achieved a good result, performance result in the classification, achieving a little a better result in the classification time. But the best result for classification time is naive-based, but in the performance, naive-based is not so good. Here we have the blip care device. It's important to note that run it again, this evaluation, because we found some errors. So this result is updated, and the results to identify the blip care device, we achieved 94% of accuracy and 9% of recall. Also, we achieved good results for bagging. So Motif was able to identify the traffic from smart healthcare applications, the random forest and bagging that are decision-based tree-based models, and they presented the best results, and the cross-validation is better than the holdout. There is a trade-off between classification time and the classifier performance, and here we have assisting on the classification of smart healthcare applications. So here we have some publications regarding the Motif method. And to adapt the network resource autonomously and achieve the smart healthcare applications requirement, it's necessary first to identify the device or application that is generating this traffic. So we did this in Motif, and this information serves as input for the Primus. So Primus has this previous knowledge on which application is generating the traffic to adapt the network resource and achieve the requirements from each application. So talking about resource allocation and requirements from these applications, we researched on the literature about techniques that try to achieve a quality of service for applications, and we found 4 main approaches or techniques in the literature. The resource reservation, but this is very static and basic and requires a signaling from the application. The traffic shaping, that shape the traffic according to the client higher profile, is very used from internet providers. We also found the traffic separation, that isolate network virtually or physically to transmit the traffic according each isolated network, but it's not scalable. And the scheduling, following priority previous to transmit the highest level of priority first. But this approach, they are not scalable, dynamic, and they do not support health traffic. So we made a question, how to achieve smart applications, because we have several devices, different devices applications, and in the middle of these, we have the smart healthcare applications. So we found the network slicing concept that offers automation, isolation, customization, and elasticity, and end-to-end communication. This is possible because network slicing is based on software-defined network and network function virtualization. So this isolation and automation is possible through virtualization techniques. So here we have a picture of how it works, the network slicing. So we have the physical infrastructure with the physical resource, computing, storage, and network resource. And they proposed services slice types. The first slice type is for massive IoT. So we have a slice with many devices generating traffic. We have the high reliable and low latency slice, specific for smart healthcare and autonomous car. And we also have the enhanced mobile broadband slice that's specific for augmented reality, video streaming, and many others. So we can create specific slice with virtual resources specific to achieve that requirements from each application. So we researched in the literature about network slicing approaches using in the smart healthcare context, and we found some works implementing the service slice type, but they did not achieve low latency, or they did not implement a realistic network scenario because they did not consider virtualization techniques. We found works presenting an architecture for network slicing, but they did not implement network slicing. It's just an abstract level architecture. And we also found works proposing end-to-end slicing approach for dense urban scenario, for instance, but they are specific for IG, or they do not consider heterogeneous network, or they only consider priority transmission. So we found a gap in the literature and we proposed the Primus architecture. This is the overview of the scenario of Primus. So we have smart applications, different smart applications generating traffic from a smart home, from a smart hospital, and the Primus has the goal to transmit and allocate the resource, create slices to transmit the priority applications first and to achieve them requirements. So here we have the architecture of Primus, and we follow, here we have an example with 3 slices. So each slice has the tenants. The tenants are the users demanding that slice to run some application. So we use 3 different tenants to explain better. So we have the industry automation, smart healthcare, and augmented reality. And each slice has one controller responsible to control the resource allocation and the slice. The network slicing literature defined that each user can use up to 8 slices. So the user cannot use more than 8 slices. And here we have the architecture of Primus. So we have 3 main models. The first model is responsible to understand the slice-aware context, so understand the application context and what are the requirements demanded from each application. The mission control to understand if there are some resources available or if all the resources are occupied. And we also have pre-configured slices for the smart healthcare, because to create and configure slices take time, and then we have pre-configured slices for smart healthcare reserved. And we also propose a scheduling. So when we have ultra low latency and high reliable communication require or demanding a slice application on this slice, it receives the highest priority. And then we have enhanced mobile and massive IoT. The network slicing management model is an important model from Primus because it's responsible to control the slice life cycle. So it controls the preparation, configuration, activation, the running, so the transmission of the traffic. And when the traffic arrives in the endpoint, it makes the resource available and the slice no longer exists. So it's responsible to control all of that. And finally, we have the resource management model that is responsible to control the resource available and the resource in use. So it communicates with the network function virtualization to understand the virtual network functions available and the functions that is allocated. The models communicate through control message. So we have two types of control messages, the announce that inform the application time and requirements, and the monitor that inform the network resource available. So we evaluated the Primus in the virtualization environment. And for this, we used the mini-net Wi-Fi's because we wanted wireless technology to try and evaluate the Primus. So we used the mini-net. And we also used controllers like Onus and OpenFlow with Libera. So we created a small scenario to test the network slicing and analyze the evolution. So we have 3 wireless and 3 wired devices generating traffic. We have 2 switches, 1 access point, and we have 3 servers receiving this traffic generated by the devices. We have 3 priority levels or slices, that is the ultra low latency and high reliability, enhanced mobile broadband, and the best effort. So the best effort is a generic traffic. We consider 2 bandwidth, so with 100 megabits per second and 1 gigabits per second. And we consider 2 evaluation scenarios, considering network slicing and the priority of the slices, and without network slicing to compare the results and the use of network slicing. So to compare the isolation and the priority of this slice. We considered the workload following the literature for critical care monitoring, like 1 megabits per second for the first slice. The second slice follow a telemedicine application with 15 megabits per second. And the third one is a generic network traffic, also following 15 megabits per second, but we create threads to generate more traffic than the others. And we analyzed the latency. So here we have the main results regarding the average latency of Primus, and we have the both scenarios without and with network slicing and considering the both bandwidth. So looking for the first bandwidth with 1 gigabits, we can analyze that with network slicing, we achieved less than 6 milliseconds. The requirement demanded in the literature is 1 millisecond, but we already achieved a good result, like less than 6 milliseconds with virtualization. And the other applications, they were not harmed with these slices and isolation. And considering a more stringent scenario with 100 megabits per second, 100 megabits of bandwidth, we achieved less than 9 milliseconds in the ultra low latency and high reliability, and around 20 milliseconds for the other applications. So through virtualization and network slicing, Primus reached low latency for smart healthcare, around 6 milliseconds. The virtualization scenario with network slicing is a contribution because we found few works using virtualization, and the isolation and slicing are promising. There are some open issues regarding the network slicing, like reliability, end-to-end latency, packet losses, and the scenario evaluation. So here we assist on the achievement of smart healthcare applications through the Primus. And here we have the publications regarding the Primus architecture. But At the same time that the network data traffic and network data instrumentation can assist in identifying the traffic and achieving the smart healthcare application, it also can be used by adversaries to explore and perform attacks. So having said this, we proposed the IoT regard method that is concerned about traffic-based side channel attacks. In these attacks, in a smart home, we have an attacker sniffing the network traffic from a smart home, so close to the Wi-Fi of this smart home, and it collected this data to analyze and infer the user activity. But if this attacker explore and analyze the most relevant feature like through PCA, he can improve the efficiency of the attack because he can just analyze the most relevant features rather than analyze all the features from the network traffic. Here we present how to infer this activity from the user's devices. So we analyze the motion sensor, the sleep sensor, and the Amazon Echo. Just analyzing the traffic rate of the motion sensor, we can understand that the user go to the bed around 1 a.m. and analyzing jointly the sleep sensor, we can confirm that the user go to the bed around 1 p.m. and that the user get up around 12 a.m., so at noon. And the Amazon Echo confirmed this result because we have 2 peaks in the traffic rate around 12 p.m. So we can understand the user activity just collecting the data and analyzing to infer the user activities. So worry about the network feature exploration to improve the performance attacks, we researched on the literature about network traffic feature exploration or selection of relevant features and for what the works are using these features. So we found works using PCA to reduce the data set complexity, so just to reduce the number of features to detect intrusion or anomaly in the traffic. We found works using feature selection techniques or extraction techniques to identify the applications or devices. They learn features, but they do not apply these features to some adaptive network solution. Works using these techniques to detect malicious activities to increase the classification performance. And also we found works that try to identify eavesdropper and information exposure of IoT devices through these techniques with machine learning and feature exploration techniques. But we did not found works using feature exploration for management purpose or to develop tailored defense mechanisms. Moreover, we researched on the literature about defense techniques against traffic-based attacks. So what are the defense against these attacks? We found works masking the DNS, but there are other features besides DNS to understand the behavior of the users, like the packet size. We found some works using the VPN, but the VPN will just mask the IP address, but we can use other features besides the IP address. And they also used firewall to prevent the traffic collect from the adversaries, but some application or device demand internet connection to work properly. So it's not enough. And we found 2 well-known approaches in the literature. This approach tried to mask or obfuscate the network traffic features or the side channel data leaks. And these approaches are the fake traffic injection and the packet padding approach. The first one add fake traffic or dummy traffic and mix with the original traffic to confuse the classifier and the adversary. And the second one, change the feature values. For instance, change all the number of bytes of the packets to have the same packet size. But this work, they are specific for features without relevance, or they do not analyze the relevance of the feature that will be masked. And we have different features from the network traffic. We found one work using PCA or FA to analyze the feature importance, but they analyze the statistical feature like the average, the mean, the max, and they do not analyze the importance from different network traffic features. And there are also a concern regarding the privacy and network overhead. It's not our focus, but it's important to mention it. So based on this, we proposed the IoT regard method that work in a smart home, and we can position the IoT Reward in the app, in the access point of this home. So the goals of IoT Reward is to review the network traffic features through the network traffic capture, feature exploration, and discover our most relevant features. And then we mask these features through obfuscation techniques, the padding approach and the fake traffic injection. On the revealing network traffic features, we follow the flipper steps. So here we have the data collection. Then we pre-process these features through cleaning, extraction, some features relevant to the context. And we apply feature selection, the PCA and FA, to discover the most relevant features and use these features to understand the behavior, to perform the attack on identifying the devices, and then to mask these devices. So this refers to the feature exploration, and this serves as input for machine learning models to train and classify the traffic from each device, and then to make a decision on which feature mask through the masking approaches. Here we have the mask approach of IoT Reward. So based on what was revealed, we can mask these features following the fake traffic injection. So for this approach, we proposed 4 levels of injection traffic because we want to analyze different levels, the high, medium, low, and random levels. So here we have the values used for each level of fake traffic injection. 600, 1,000, 5,000, and from 1,000 to 10,000 fake packets in each level. And we also implemented the packet padding from Pinheiro that also proposed 4 levels of packet padding, and the authors padding the packet size, so to 100, 500, 700, and so on. We evaluated the IoT Reward through a case study. So first, we revealed the network traffic features, and then we masked the traffic features. So we follow 2 scenarios, similar to the Motif, but we have more features considered. For the packet and flow scenario, we use it only decision tree-based algorithms and ensemble because they are presenting the best results for the traffic identification. And to generate the fake traffic, we use this Capita traffic generator. We consider the holdout and the cross-validation with the parameter K with value 10 because Pinheiro also uses 10, and the performance evaluation metrics. So here we have the data set. It's the same data set considered on Motif, and Pinheiro also used this data set, but the data set was updated. So now we have 31 devices, and the devices that generated the small amount of traffic is the smoke, a smart plug, and a blip care device. And the devices that generate the biggest amount of traffic is the Wemo switch, gateway, and a monitoring camera. To generate the fake traffic, we create fake devices. So for each real device, we create 1 fake device. So we have 31 fake devices. So mixing the real with the fake, we have 62 devices. So about the feature exploration results on revealing the most relevant features, we can analyze the PCA results of the packet scenario, where we can analyze the contribution of each feature, network traffic feature, and we can observe that the number of bytes achieved almost 30% in the contribution, followed by the timestamp. And when we analyze the dimension or the PCs, the principal components, we can understand that the first PC represented by the number of bytes achieved almost 6% of variance on representing this data set. Something similar can be seen in the flow scenario. So we have more network traffic features because we are analyzing flows, but we have the same proportion of contribution from time-related features and the number of bytes and number of packets. The flow duration and inter-arrival packet time did not achieve a good contribution because the representation is all made by end timestamp and start timestamp. Analyzing the variance contribution, we can understand that the first and second PC presented the most variance, followed with the third PC. So it means that the timestamp and number of bytes and packets achieved the most representing results. But when we analyze packet scenario and flow scenario, we understand that the number of bytes or the packet size represent the most relevant Information because the factor analysis showed something similar. Here we can analyze that for the first factor, the number of packets and number of bytes achieved 99% of correlation, representing 71% of the variance. And this can confirm that the packet size is the most relevant feature, followed by the timestamp features. So we decided to identify the devices in other words to perform the attack, considering all the set of features and just the key features, in this case, the number of bytes, because we are in the packet scenario. So we can observe that the classifier performance, it not reduces so much when considering only the number of bytes, just reduces 7% in the classification performance, considering the precision. So we achieved a good performance considering all set of features and also just the key features. So the attacker can decide only to use the key features to perform the attack. We also analyze the masking approach. So here we are analyzing the masking approach following the fake traffic injection. And we have the 4 levels of masking of injection traffic. And here we have a surprising result because in the literature generally most masked is the most highest level of obfuscation, and here we get something different. We achieved best result in the lowest level because we generated around 18,000 of fake packets. This number is updated according to the manuscript. So in the lowest level, we achieved the best result, and the second level also achieved a good result, reducing the classifier performance when comparing with the previous classification results. And the random and the high level of fake traffic injection improved the classifier performance because we increased the samples used to classify the traffic. So we improved the results for the classifier, giving more samples. So we understand that the better results is from the lowest level. But when we look to the packet padding approach, we have, which is consonant with the literature, because the highest level of packet padding achieved the most, the better result, like 10% of classification performance. So it can be compared with the MTU. The MTU is a very well-known literature approach of packet padding because it increases all packet size to 1,500 bytes. So all the packets will have the same size, and then it's difficult to the classifier understand from who is each traffic. But we also can analyze the cross-evaluation results because we are talking about unbalancing data, and the cross-validation is a good solution for this scenario. So achieved a better result than the holdout. And we also can compare the fake traffic injection approach and the packet padding approach, only considering the packet size and the statistic features from the packet size. So we can understand that the lowest level of fake traffic injection had achieved a better result than the lowest level of the packet padding. And it's important to point this because in the IoT, we need to consider the network overhead. So how much the traffic injected or how much increased the size of the packet size will increase the network overhead. And we are talking about IoT, we cannot increase so much the network overhead because we have critical applications. So although the highest level of packet padding achieved the best result, considering the network overhead, we can point out that the fake traffic injection achieved a better result when compared with the lowest level of the packet padding approach from Pinheiro. So based on this, we can say that the IoT regard explored and revealed the most relevant features, in this case, the packet size. It performed the attack, the traffic-based side channel attack, only considering the packet size, and masked the features, achieving a better result in the lowest level of the packet padding approach. There are open issues regarding the feature exploration and the privacy versus the network overhead. That's important to analyze the network overhead and compute this information. So the IoT regard assisted on improving the user's home privacy and the security. Here we have some indirectly related publication regarding the traffic-based side channel attacks and a submission. So finally, we can talk about the learned lessons and the future works and the conclusions of this work. So the main hypothesis of this work is the IoT network data instrumentation and feature exploration to support network security and performance actions. And the main contribution was the novel methodology for network data instrumentation as a prior step for network management. And we can say that because the Flipper methodology supported the Motif method with some steps. The Motif method, the result of Motif method and the network instrumentation supported the Primus architecture, and also the network data instrumentation and analysis supported the IoT reward method. So yes, it supported the network management. Answering the research question, is it possible to create a broader methodology for network data instrumentation and to support different purposes like network performance and security? Yes, because we propose that Flipper and Flipper can assist both network performance and security management. If the instrumentation of data assists the identification on which application or device generate traffic, yes, because we perform a network data instrumentation and analysis as input to the Motif method to identify the traffic that's generating the traffic. And also this knowledge, this previous knowledge about the traffic, the application that is generating traffic, assisted the achievement of smart application requirements because Primus used this information as a previous knowledge. It's important to note that we did not connect Primus and Motif, but we assumed this previous knowledge. And based on this knowledge, we were able to adapt the resource, create slices, and transmit priority to ultra-low latency and high reliability results. Finally, the network data instrumentation also can be used by adversaries. So the adversary can understand the most revealing features and perform attacks using these features. So he can improve the performance of these attacks just using relevant features. So he did not need to use all the features from the network traffic, reducing time in his attack. And also the network data instrumentation give valuable information to develop tailored network security mechanisms. So the IoT reward method can mask all the network traffic features, so can mask only the packet size as shown in our results. So finally, we have the learned lessons from this thesis. Network data instrumentation and feature exploration, they are essential for network management because they can assist the knowledge on what device or application generate traffic, assist in data-driven decision, customized service, adaptive network resource allocation, mask the relevant features from the network traffic, development of tailored defense mechanisms, and the management of security and performance. Also, we have some future works regarding the evaluation in other scenarios. A more realistic scenario with network slicing in another technology communication, network overhead versus privacy for the network traffic-based attacks, the classification time, the low latency, and also analyze the reliability. So thank you very much for the time. Thank you for my advisor, co-advisor, co-authors, and colleagues. Thank you very much.
Thank you, Andressa. I think it was right on time. Yes, 45 minutes, it's okay. Thank you so much. So now we go to the second step of this defense. First of all, I would like to thank Annelise, Leobino, and Wagner for being so kind and accept this invitation to participate in the jury committee of Andressa. Annelise also participated in the first step of this work. We changed it a bit and we focus more on the data contribution of that. So I will then ask, I would start with Leobino to make the considerations, but I think I go to Annelise for starting your considerations of this
As you prefer, Michele. For me, it's okay.
I think I will go with the, yeah. Go ahead. Thank you so much.
Okay. Thank you very much, Andressa, Michele, and Burak for the invitation. Yes, it's true. I already participate of the qualification jury, and I think I can say that the work progressed a lot after the qualification. And thank you very much for inviting me. I start by congratulating Andressa and her advisors for the excellent work done. I think the document is very clear, very well written and well detailed. Andressa gave an excellent presentation, very quickly, but excellent presentation, Andressa. Thank you. This presentation demonstrates your deep knowledge in the area, and I think you done very, very good work. And I would like to congratulate Andressa for her relevant publications, include the highly relevant international journal. I think it's a very, very good results. I already sent you my questions and comments if you prefer to look, or I think it's interesting to open the document, because I have some points to some comments and suggestions about the document. Probably it's better to follow if you have the document open. If you could,
yeah, I'm opening
document.
here.
Yeah, I think that the whole document is very easy to read. I think it's very easy, and it's a great read, and no problem about this. I can find only a few typos that I put in the document that I sent to you. Very, very few typos and some small errors in the text, but it's a very, very well done and well written document. I think the main questions is about. I think you had a very good division of and balance of the chapters. I always start with looking for the different chapters that you can devise your contributions. I think you are very good on it. I really like your introduction, because you present your motivation and questions, research questions, that it's very important before present a work. I think it's a very interesting manner to present your work, and the contributions as well. I think the background section, it was very, very interesting also, but I think that you can move the related works in it's my suggestion, in the beginning of the chapters to the chapter 2, because it takes a long to start the contribution in the chapter, and when we start, we would like to see your contribution. I really enjoy your table about. I put all these things in the text. I really like your table, and you compare all the works and with your contributions. I think it's a very, very good table that you include, but for me it's you can concentrate all the bibliography, background, and related works in the chapter 2. I think it's easier, because sometimes, for example, in I think section 3.1 and section 2.2.4 have repeated text, and you don't need to introduce again the same concepts if you concentrate all the related works in chapter 2. I agree that is interesting to present according you start a new contribution, you present the related works because you can place better your work. But I think it's too long to start, and in my suggestion, you can move all the related works in the chapter 2, and finally in chapter 2 include also the where you place your work comparing with the other related works. I think you can do this in the chapter 2, but it's only a suggestion. You can discuss after with your advisors, but it's not a big deal or a big problem. I think it's only to easier understand your contributions. I think only about the text, I list some typos then, and you can move in the text, but I think it's you really do a very good work. I found, for example, in section 2.2.4, when you talk about the traffic identification approaches, it's very extensive and sometimes could be summarized because you expend a lot of time and a lot of to explain some approach that you didn't use after. And I think it's interesting to summarize only to leave your document easier to follow. I think only a correction in page 60 is table 3.1 and not table 4.1. I think it's only a mistake. And I think it's a very good also extends list of reference. Also, it's a very good work, Andressa. About the technical questions, we start with the title. When you talk about data instrumentation, I understood the concept and the term, but I look for the definition in your reference by Sarker or Verma. You create the term in this, you use this kind of thing, organize, clean the data, but data instrumentation, I didn't see the definition in this reference. Did you create this term?
It's not a creation because I saw this term from big data analysis. So maybe I used it, I forgot maybe some reference, but when I reference Sarker is because this reference talked about a lot, so about the importance of do this preprocessing. So cleaning, extracting, preprocessing. And when I used this reference was to show that it's important to do this. This was my goal using. But this term I did not find in network traffic analysis, traffic identification. I really did not find. But it exists in big data analysis when I found works using like MapReduce, using other techniques from big data analysis. So it came from there, but a definition and following this methodology that I created did not exist. I created the network data instrumentation following these steps for IoT because I understood that is important because assist and support different network management. And it's important, these steps, to understand the context, preprocess, clean. So I was using different steps and connecting each other to make sense for the network traffic management and analysis in IoT. But yes, exists, but from other concepts.
Okay, I really like these terms. That's why I asking you, because I already seen other data analysis, but not in the same definition than you use here. And when you see it there, that's why probably you need only to clarify or when you define this term in the chapter 2, I think you cite the reference by Sarker and Verma, to explain the definition of this term, and I think you can explain a little bit more equal than you make now. Explain a little bit more this use of this term. I think you can input, because it's not in this article, in these papers. If you look for in these papers, there is no data instrumentation in these references, only to clarify this term. But it's I really enjoy this term. I think it's a very good use for it. After I have my list here, page 64, figure 3.2. I don't know if it's better to put here it's the architecture of Motif. When you present the access point, the router, and the inside the network, where you, I don't know if you prefer include or it's okay. The idea of the install the Motif is on the router inside the user's home. Where exactly you
the position of Motif?
Yes, where exactly? Because if it's inside the home, the user home, this user could already directly identify the device, you know?
The idea, I suggested in the manuscript and in the thesis to position it inside the home, because, for instance, if I put in the access point or in the router of the home, it's because all the IoT devices generate traffic to it. So to the app, to the access point, or to the router. So it needs to be a point that receives all the IoT network traffic to identify this application. And it's necessary to be in the edge and not in the core, because we need to identify this application to support on-premise. So to create the slice after and to achieve some smart healthcare application, or to be able to do something before to transmit, is important to identify before initiate the transmission. So I suggested put into the smart home, yes.
But because if you put inside the smart home, because the Motif, if I understood well, is responsible to identify the applications and from the IoT devices. And if you put inside, you need to that user agree with this implementation. And in this case, you cannot. Because for me, it's like you already have the agreement of the user to put inside your method, but to identify some devices that you already can do it. No, it's really need an application identified inside the user. I would like to.
Are you saying about the user has knowledge about the collection and identification of the device, right? Yeah, it's important the user know and has this knowledge, because we are talking about a smart home, is his private space, so it's important. And also it's important he or her to know, because we are collecting his data. But I think in other way, because in the scenario that we have some user being monitored, like an elderly user or a patient that did not want to be in this hospital but want to be at home, to be monitored in the home from his bed, he will accept this, because it's important to him stay home, stay in a comfortable way from his home, to be monitored by his doctor from the hospital. So he did not to locomote. So I thought in this perspective about the quality of the life of the user. And yes, he needs to agree, because it's the same. When we identify the traffic of an application, it's interesting to mention it because at the moment that we identify this traffic, if the user did not know, we are performing an attack, the traffic side channel attack. So because of this, I have two lines in the thesis about performance and security, because at the same time, the identification can be used for a good reason, like monitoring, improve the quality of life, and improve the requirements. It also can be used by an attacker. So we have two perspectives. I don't know if I answer you.
Yes, great. And in this case, how safe is the Motif method? Because could the Motif method be attacked by outside agents, for example? Because it aims to identify the internal device of the network and identify well the devices. And do you you are worried about this safety?
We did not worry about this because we are just worrying about to protect the user data from his home and to collect this data to identify some device. But through the masking approach from IoT Regard, we can protect. So if an attacker can try to get this information, identify the traffic, the data will be masked, so obfuscated. But let's imagine a scenario like you say, the Motif being used by an attacker. Yes, he can perform an attack by Motif. This is possible. But when we use the obfuscation together, then we are using some kind of defense. But we achieved a good result, reducing the classifier performance in identification of the traffic. But still, there is open issues regarding this classification performance. Because of this, is important to analyze the features, and then you can mask the relevant features and protect, let's say, more the network traffic.
Okay.
So this is the type of defense security mechanism that we thought.
Okay. And after in the same chapter, section 3.4.4, can you explain again how you identify each of the devices? Because you already know, in this case, the behavior of the 9 devices, yes, that make up the scenario, and so you can identify. But if you don't know exactly these devices, how you can identify?
We used the MAC address to have this knowledge about the traffic from each device, and the MAC address serve as the ground truth information. So we follow supervised algorithms. So we use it labeled data, and we use the supervised algorithm because to identify smart applications or generic applications, the literature indicate to use supervised algorithms because it's more probably to achieve a good result than unsupervised, because in the unsupervised, we can have the Skype and the telemedicine. And the telemedicine can have, can use another type of application rather than Skype, and Skype will have a huge amount of traffic. So probably we'll group the telemedicine traffic with the Skype. And this is the literature saying, so we decided to use the supervised with the MAC address as the labeling. So we divided the data set in training and test. So we have the training data with the label and the test data without the label. And we follow this methodology to saw if the classifiers identify this traffic, just considering the network traffic features. So in the testing data, I just have the packet size, the mean packet size, minimum packet size, and this is formation without the labeling. So in this way, we identify the device.
Okay. After the figure 3.5 to 3.8, you show, and in presentation also, I think it's slide 25, you show the lower performance of naive Bayes. Do you consider it is interesting to continue evaluating this machine learning algorithm? Because even consider the figure 3.9, the NB algorithm was the fastest in the terms of classification time, but the classification performance was very low and not desirable for the health context. Do you think it's really interesting to evaluate this algorithm? It's still interesting.
Maybe we can think in a scenario using, because okay, in the flow scenario, the naive Bayes did not achieve a good result because we have less amount of traffic of samples because we group the packets into the same in the flow, so we have less samples. But in the packet scenario, we can saw in the slides 25 like 63% of accuracy. It's not a good or the better performance result, but it's a result. Maybe can be improved by other features by using or combining and not. I saw a scenario using more features, but at the same time, we have, for instance, the random forest that achieved a really good result for both scenario, packet level and flow scenario, with 38 seconds. Okay, it's a huge difference when comparing to naive Bayes, but it's not so bad.
It's not fair.
Yeah. But in the final of the motif, I suggested to combine the flow scenario with cross-validation, because cross-validation achieved the best results in performance result, and we are talking about IoT, so unbalanced data is better the cross-validation. And the flow scenario analyzes small amount of samples, so we can mix the scenarios. But the naive Bayes, I don't know, because he presented a poor performance, so it's a considerable. It's important to consider the classification time because we are talking about smart healthcare applications, but it's also important the performance. So maybe a mixed scenario can improve these results.
It's interesting that my follow question is about this conclusion of chapter 3. You say that based on this result, the cross-validation method fits in the health context, only needing further studies about classification time. However, my question is, this classification time does not make this method difficult to implement, making it unfeasible. And,
I think sorry, you did
no, it's only to I start to think about it. Sorry.
Okay. I think can have a cost like the classification time, but at the same time that has a cost, it's important this previous knowledge. I also think it's important because without previous knowledge, we will implement network management solutions without knowledge. So they can be static, they can be tailored for a specific context without previous knowledge. So we did not follow the better way to develop a network performance management or security. So we have a trade-off between the cost to implement this classification. But looking to the valuable insights that we can get, I think it's most important to improve this classification time and performance to use for network purpose, because look to the data is very, very valuable. We can get so much information. So why did not look? So I think it's important to improve these results.
Okay, great. After in section 4.2, you say that unlike the literature, Primus adapt network virtual resources and rules according to smart applications demand. But in the case of area SVP, you also adapt reserve resources according to the applications. It really is static. It's not the same thing, but you only to point that you have already some models or architectures that provide the same idea. It's not the same that you provide because it's dynamic and adapt to the context. But I think your contribution is more than this, because it's not only adapt to the resources according to demand, because this is, for me, the RSVP already done. And it's a statistical way, not very good in scalability terms, but it's already done. Only the affirmation, I think you can, I put in the text, I think you can improve this, your statement, because it's not really only this. I think it's more than this. You have already mechanisms to improve this, and you do, or your contribution done more than only adapt the network according to the demands.
Okay, I can improve this.
Okay, and after you say after in section 4.2 that the connection between Primus architecture with the Motif Method and Flipper is also outside the scope of this thesis. But it's not interesting to include at least a discussion about this integration, or you think it's too difficult, or because it's a very interesting to think about how to connect these architectures. And I think as you present, you can see the outside, the output of the Flipper file inside to input the other architecture. And I think this integration or a discussion about these three methodologies could be, or all the methodologies that you propose could be interesting. I think it's.
I agree. I try to put this discussion in the text, but I not was successful, because in the Motif and IoT regard is very clearly because we use some steps from Flipper. IoT regard use all of the steps of Flipper to analyze the data, pre-process, and extract the most relevant features. But the Primus connection with Motif, we just assume the input of Motif to the Primus, because we were in a virtualized environment and we were worried to perform and evaluate the Primus architecture. So we assume this connection, but maybe we can discuss a little bit how this input data achieve in the Primus and how he can use this information. Like, okay, it's arriving in application and the user is demanding this slice to generate this traffic. So how
discuss about the limitation, discuss about
I can improve this discussion.
I think it will be very interesting to include this, because we can think about the whole architecture and could be implemented in this case, but we need to discuss or think about the limitations also. Okay, in the case of the network model of the Primus architecture that you put in the section 4.2.1. It is necessary to previously know the set of applications and the traffic associated with each of them. Is that correct? In addition to the number of end users. You need all these informations before input to the architecture.
Yes, correct. Yes, because I think I see you, because let me explain. We need to know which application is demanding that slice, because based on the application, we will know the requirements of this application. So, okay, it's arriving a ultra low latency and high reliable slice that is from a remote surgery. Okay, we
to
have
match with the slices,
so we need to know the application and the traffic that belongs to the application, but we need to use that traffic to transmit in this slice. So this information is important. And the user is a network slicing definition, because each slice can have just 8 users. So it's important the user that is behind that slice to have this control, because otherwise some user can monopolize the slice or use more the slice than this its yellow. So there are important information for primos.
Okay. The next question is about the do you think about any kind of shaping in the Primos architecture? Because especially when you just say that each slice allows up to 8 users per time. Do you think, because you discussed traffic shaping before, when you discuss about KOS mechanisms, and here in Primos architecture, do you think about, or do you think it's important to shape this kind of, because you have the control admission in your architecture, but I didn't probably, or I cannot see because I lost the information, but I cannot, I think it will be important a shaping also, no, in your architecture.
Yes, I think it's already been done some kind of shaping, but we are not using the traffic shape conception. But why I say that? Because each slice is using a specific amount of resource to achieve some application. So we are already doing some kind of shaping. Yeah, we are reducing the amount of bandwidth or increasing. So we are doing something like this. And
before the admission, before the control admission,
because we decide, okay, so you need to transmit in like 1 millisecond, 90% of reliability. So okay, you will be need I don't know, something of resource and some value for bandwidth and go on. So yeah, we do this resource allocation following a kind of shape.
Okay. And about the emulated scenario presented in figure 4.4, do you think the results were influenced by the limited scenario? Because you have a small scenario and your application is for probably you have in a real scenario, you have a lot of more than these users and applications. Do you think that your results follow the same trend if you had a scenario with a higher number of users and a heavy traffic?
Yeah, this is a small scenario because we wanted to test network slicing, because that is a difficult and is a task. It's a difficult task to implement the network slicing with virtualization. Because of this, there are a few words implementing slicing with virtualization. But we try to implement a scenario with an stringent scenario with a huge amount of traffic. Because of this, we use the third slice, the best generic traffic slice, the best effort, to increase the amount of traffic, and we use it to smart healthcare applications. But yeah, I believe we need a more realistic scenario to understand better the network slicing, like with a lot of IoT devices, and also using different technology communication. Here we use it wired and wireless, but it's also important to test on 5G with some other tests to analyze and implement the latency, because the literature say that 1 millisecond will be achieved with 5G. But when we saw the works, they are using some kind of priority without slicing. Then they achieve 5G, 1 millisecond. But it's difficult to implement a realistic scenario with network slicing. But maybe a more realistic scenario will have other results and more realistic results.
Okay. I almost finished. Sorry about the long time. I found the discussion and limitations section at the end of the chapter 4 very interesting. I just think that you could better discuss the implication of these limitations in your proposal. I think because you explain the limitations, but you're not, this limitation is not directly you directly explain concerning your proposal. I think you could input, if it's not so complicated, to input some discussions about each of the limitations that you explain, and comparing or placing according your contribution. I think it's only a suggestion. In chapter 5, you can explain a little bit more how EOT regard identify the EOT devices, because you already have this information before. Is that correct?
We do not use the output of Motif in IoT regard because we improved a little bit the analysis. So we extracted more features from the network traffic, and we use different machine learning algorithms. So because of this, we consider it as another analysis. And also because in Motif, we did not analyze the most relevant feature. In Motif, we just capture the network traffic, extract features, clean, preprocess, and okay, serve as input for the machine learning. But in IoT regard, we added one step about discover the most relevant features and do this analysis. So we perform again all the step of Motif, improve it to get more information from the traffic and to perform a more deeply analysis, we can say.
Okay.
Because of this.
Okay. After you on page 112, you explain, you input the feature selection. Could you explain a little bit more how it works, the feature selection? Figure 5.6, I think.
Oh, yeah. So we have a data set of features, network traffic features, and these network traffic features, it's analyzing the contribution and the variance. So both PCA and FA analysis, they analyze the variance of each feature in the data set. So they compute this variance comparing to the other features to analyze and to get the features that has the most that represent the most variable information. So the features that has most variance percentage, they represent more the data set than the other features. So these analyses use the covariance matrix, variance, and the aging values. So as much as close to the aging values number 8 or higher than number 8, number 1, and as much close to the number 1 of aging value, most variance that feature will have. So most relevant this feature is. And this the FA can give to us, and also PCA also analyze this variance. So based on this, we understand the most relevant feature. So to do this, we perform both analysis, and we also look to the graphics. So because of this, I show so much graphics in the manuscript to show which are the most relevant features and why they are so relevant, considering the contribution and the variance. And then we can remove, for instance, in the flow scenario, the analysis showed that we can remove the flow duration and interarrival packet time, because the representation of the data set is already showed about through the packet size, the number of packets, and the end and start timestamp. So it's analyzing these statistics to understand the most represented features. And then we select just the most represented to identify the devices. And then we also try to mask just the packet size to saw what happens.
Okay, great. Also, I think it's in page 119. it will be interesting to include some details about the algorithm that you were implemented. I think you only list the algorithms. I think you could only explain a little bit more. After in page 20, sorry, about the obfuscation techniques, I always, when you have some parameters or values, my question is, why these values in table 5.4, where they are chosen? You put, I think it's in page
table 5.4, yeah?
4, yes.
In the 121 page.
21, okay, yes.
It's because we defined 4 levels of fake traffic injection. We defined these levels because it was not the focus of the thesis, the network overhead, but at the same time that we are injecting traffic into a network, it's important to understand the different behavior. So because of this, I created 4 levels. So I call it the low, medium, high, and random level. But here I'm using numbers. I need to update this in the text. The 600 is about the lowest level, 1,000 is about the medium, 5,000 the highest, and then the random, because I think, okay, I will put a random number of packets for each device from 1,000 to 10,000, because I want to analyze the impact in the fake traffic injection, and because I was hoping that some lowest level will achieve a good performance. So in a lowest level of injection, we are not increasing so much the fake trafficking into the network. And because of this, we created the levels. And for each fake device, we generated, for instance, for the first level, the 600 fake level, we generated 600 packets for the device. So we generated 600 packets for each device.
I understand that you divide in the 4 types, but I would like to know if would it make any difference in the results if you had chosen this value, for example, the last one 60 in 600 fake packets per device. If you change these values, 600 to 6,000, is different in the results. Of course, the others the same, 9,000, 1,000 or 1 million. I don't know if you multiply by 10 or by 100, the results was changed, because why choose these values exactly?
Oh, I see your question.
These values are from the one reference or from the literature? I don't know.
No, we decided the values looking to the results. So we run the results, and we were increasing the number of packets in the hope that will improve the result. So we started with a less amount of fake packets, and we start growing up the amount of fake packets, because we were thinking that will improve the results, reducing the classifier performance. So in contrast, increase the classifier performance. Because of this, we stop. We stop in the random from 1,000 to 10,000. But I don't know, you are seeing my screen? So about this result, I can answer you about the amount of fake traffic and the difference in the results. For instance, let me put in this screen, that is better. So here in the lowest level, we generated around 18,000 packets, fake packets, from the 31 fake devices. And in the second level, we generated 31,000 packets. So we generated a huge amount of traffic when compared to the lowest level, but we have similar results.
Okay.
Yeah, but when we look to the 5,000 fake level, we have 155,000 of fake packets. And then we start to increase in the performance of the classifier. So I stop. I didn't know. I will not increase the fake packets.
Okay.
But yeah, using until 30,000 of fake packets, we have a good result. Maybe can be interested to analyze with less amount of packets, like
yes.
200.
200, 100, for example, only to see that it's the same results. You can reduce a lot
more levels.
your amount. Yeah, yes.
I agree. Can be a good idea.
Okay. After the tables 5, 6, and 5, 7, how did the values get so different? I think it's the next, no, which one in the page?
In the next page?
It's table 5.6 and 5.7. 5.6 here in page 125 and 126. Then you have the PCs and factor results from the two scenarios. How did these values are so? Could you explain a little bit more about these results? It's so different in the. Of course, each PC is analyzes some informations, but it's a very different. I don't. I would like to understand a little bit more this table.
Okay, sure. For instance, in the table 5.6, the DPCA and the DFA they show the correlation between the features. So in the first PC, the PC1, we can saw the number of packets and number of bytes with 70% of correlation. So both of these features, they are very correlated because they are related to the number of packets and number of bytes. They are similar. So they are very related and they represent the PC1. But the other ones, the timestamp and inter-arrival packet time, they do not correlate with the number of packets and number of bytes. But when
because
we look
in PC1, not correlated this information.
Yeah,
yes.
But they are correlated in PC2. So in the PC2, we have the time-related information with a high correlation, but then the number of packets and number of bytes, they are not correlated because they are not correlated with the time-related information. So they group the most relevant features for each PC. So the first PC, the cumulative proportion of the representation in the PC1 is 50% because we have two features representing 70%. So we have a huge proportion of contribution. In PC2, we have the cumulation 82 because the proportion of variance represent each PC. So we sum the PC1 with the PC2, the proportion of variance. And then we can saw that just looking to the PC1 and PC2, we already have 82% of contribution. So we have a huge value of contribution just analyzing the number of packets or bytes and the timestamp and interpacket time.
Okay.
And the 4PC is not so important because we don't have a huge correlation. And this is also represented by the factor analysis. So in the first PC, we have the packet and size related information. And for PC, F2, the factor 2, we have the time related information. But for the flow scenario, this changed in the table 5.7. Because I understand with this result that for a flow scenario is important the time-related information because we have the first packet with the end timestamp and the last packet with the end timestamp. So it's important to understand the timestamp of this flow because a flow has several packets belonging to it. So the time-related information is presented in the first PC as the most relevant information. So we have the start timestamp and end timestamp because they are very related. And also we have in the PC2 the number of packets and number of bytes. So analyzing this correlation, we also can understand that we can, for instance, we can remove the number of packets and just analyze the number of bytes because they are highly correlated. So it's not important to analyze both of them. We can analyze just one of these features. And this kind of information, the PCA and the factor analysis give to us. Understand the features, the correlations, and what is important to analyze and not to analyze.
Great. I think it's quite interesting, the application of statistical techniques in this chapter. Very well done. I think it's a very good contribution also. And the last one, the last question and comment, the fake traffic injection and packet paging are popular and interesting approach, but however, the cost of terms in terms of energy consumption, increased use of the link, higher error rates could not make these techniques feasible. In the case of EOT networks, what do you think about? Because if we think about, it's a very useful approaches, but in this kind of scenarios, in EOT scenarios, we have a very constrained devices and bandwidth, and also energy consumption. What do you think this approach is really used in these scenarios?
I agree with this affirmation because I wrote it, but because of this, the cost, the energy consumptions, there is still an open issue regarding the privacy and the network overhead, because when we are talking about IoT, we have a sensitive, private, and critical scenario. So at the same time that is important to mask these features to protect against these attacks, it's also important to think about the network overhead, because imagine you are at home, but your bandwidth is overload because you have fake traffic. So this is an open issue, but I try to improve this masking approach, not proposing a new one, but to use the relevant features for this solution. So thinking about this trade-off, I thought, okay, so maybe this defense mechanism can just mask the relevant features and let the others. So we do not need, it's not necessary to add a lot of traffic. It's not necessary to increase in a huge proportion the number of bytes of the packet. So this was my effort, trying to show to the mechanism, to development, the most relevant features to mask just this one and not mask all the network traffic in order to reduce this not network overload. But still, it's necessary to analyze this more deeply, like how much each one increase in network overhead, and which one is, because we analyze it, how much each one decreases the performance classifier. But talking about network overhead, this is also important. But we cannot forget about privacy. And because of this is an open issue in the literature, and there are many works talking about this. So need more study about this and a better solution. Maybe the most relevant feature can assist, like I show in the results, but still needs improvements.
Okay, great, Andressa. Finally, once again, and I would like to thank you for the invitation to participate in the jury, and congratulate you and your advisors for the excellent work. Thanks again.
Thank you. Thank you very much, Professor.
Thank you so much, Professor and Ms. It was very insightful comments that you have done. So I took notes. I think Andressa also took notes from most of them. So we will consider after about the suggestions and the comments. Thank you so much. Now we go to Professor Leobino. So before passing to Professor Leobino, Andressa, when the professor points any figure or table, I think it's good to show here to the other professors be able to follow. Okay.
Yes.
Thank you so much.
Yeah.
Yeah. So go ahead, Professor Rubino. Thank you so much again for your kind acceptance on this to be part of this jury committee.
Hello, everyone. Can you hear me, right?
Yes.
Can you hear me? Yes. All right. So thank you very much for the invitation and for the opportunity to be part of this jury. I'm really happy to have the possibility to contribute with a work advised by Michelle, is a professor that I've followed the works and admire a lot of things that she has done in IoT, and also the opportunity to know the Professor Burak that is also advising this research. Also, I congrats Andressa for her presentation, quick presentation, and also for the work that she has done. First of all, I'd like to say to you, Andressa, that you have a thesis here, so don't worry about my comments.
Thank you.
I have a lot of comments, but I will try not to follow every comments, because I will send you my PDF with my comments, and I will go through the most important aspects that I think that deserves some discussions, right?
Okay.
I also took notes of Annalise comments. I agree with most of them. And then I also understand some of the questions that she has made. And then I also agree that repeated definition of concepts is something that sometimes is fatiguing, is tired to read. Sorry because I sometimes I mixture French with English. But sometimes repeated definition is tired for reading. So I think that you have to think some part of the text, because in general I used to say to my students that when they make some mini reference from the middle to the end of the thesis, something is missing on the beginning. And then, so I think that you can move some definitions that you are trying again to the first part of the thesis. This would improve a lot the reading. And I'd like to start, because I believe that acknowledgement is something very important. I used to go to the thesis and to go to the acknowledgement sections, and then I missed it. So acknowledgement section in order to know the people that has been important in your process. So the persons that contribute to this work in general we see on the acknowledgement sections. So I would be happy if you put acknowledgement section in order to share with the audience and the reader the people that have been important for your work. All right.
Okay.
Also, I also believe that science. I've seen that you have done a lot of things in your thesis, in your way to the finish. But science is more like what you have learned than what you have done. And then I'd like to know what you have learned throughout this process.
Yeah, I agree with you. What I have learned in all this process is that network data instrumentation and network traffic analysis is very important, because all my thesis for over the 4 years, I was seeing that it's important to get valuable information. It's important to get previous knowledge, or it's important to have a smart data-driven decision. when we look to the data, we can get valuable information to make a smart decision. But when we do a decision without to look the previous data, we are not making a smart decision. So this influence in the network management. So when we are talking about the network performance management, security for develop adaptive solution, it's important to have a previous knowledge. So what I have most learned in the PhD is that to look the data, collect this data, look carefully and deeply and understand the network traffic data and how this can be used, get valuable insights and use this in the better way, it can help several solutions. So this is the most important learning.
All right. The most important lesson in this process. All right.
Oh, yeah.
So let's start with the most concern that I have, that Annelise also asked you, but I was not convinced yet about your explanation. It was related to data instrumentation definition. I used to work with network measurements way back when I was a student, and then when the first years of my research career. But when I saw the instrumentation definition, the concept the instrumentation, I got really excited, because in networks in general we use the term instrumentation as a way to put devices in the network to get data. Mm-hmm. And then when you said data instrumentation, I got a little bit confused. And then I noticed that you and then you explaining to Annelise that you took this, at least you were based on the definition from another area, mm-hmm. right? Mm-hmm. So, but I also went through the reference that you made here, mm-hmm. and then I also agree that I didn't find the definition of data instrumentation as mm-hmm. as you use in your thesis. So I asked to myself, she has introduced these terms, and then you said here that you were not introducing this term. This is from another research area. But even when you use MapReduce, these techniques, I'm not from this field, yeah. but in general, is what you do with the data itself. And then what you are proposing here, at least as I understood, is a process that you follow for the data instrumentation, not the data instrumentation itself. Is that right?
I will explain what I try to explain with the network data instrumentation in the manuscript. Network data instrumentation, I just found in big data analysis. Right, this is right. I did not found in network traffic analysis. That is it was my field. So I did not found. When I found the instrumentation, the term and the definition in big data analysis, this term was used to structure data, because they define 3 types of data: unstructured, unstructured, semi-structured, and structured. So to achieve this structure, it's necessary to perform some pre-process. Then, because of this, I create the methodology Flipper, called it as a network data instrumentation, because I want to achieve a structured data to get valuable insights. And to achieve this structured data, is important to understand the context, clean, pre-process, and go on. This is the definition inside the thesis of network data instrumentation: to perform a sequential of steps to achieve a structured data and get valuable information. But I just found I researched in different fields, and I just found, maybe I can look more, but I just found in big data analysis, structured the data set as input for tools. So this structuration is the pre-processing, cleaning, and this step. So I bring this term to my contest. This is what I did.
That's the point. I understood the first understanding of you that actually data instrumentation, it's what you do with the data.
Yeah.
To support other application. So in order to facilitate our discussion today, that's one of the reasons I ask about the language that we will be discussing here, because I think that it's crucial point of this thesis. Because of the title of the thesis, you use the terminology data instrumentation. So for that reason, I think that we should be careful with the use of this term. And at least you have to put a discussion here, a chapter here. You use a single paragraph to describe. I think that it deserves a chapter to discuss data instrumentation, because the title of the thesis is data instrumentation. So then it's not clear for everyone what is exactly data instrumentation in this context. So I think that it deserves a clear discussion about data instrumentation. I think that one of the reasons Annalise has asked to you about it.
The question, okay.
This question, and also related to data instrumentation, I have another concern related to the language also.
Okay.
It's about the methodology. You said that Flipper is a methodology. Why you describe it as a methodology? Let me explain to you why I have doubts about this. Because in general, when you have input output in a sequence of steps, we name it as a process, or at least as a workflow. And then you use a workflow to define your methodology. And then I got confused about this. So have you discussed with your advisor or with your colleagues what exactly Flipper is a methodology? Have you discussed about process or about simply workflow?
Yeah, we have discussed this. And the first term used was a workflow. I was in the doubt between methodology and workflow, because when I start creating the steps and the sequential steps, I thought, okay, we have a sequential set of steps, so it can be a workflow, because flow are sequential steps. But then it also can be a methodology used by different network solution adaptive network solutions. So can be a methodology of network data instrumentation, a methodology on how to understand your data and get valuable information. So at the same time that we follow some steps, I understand that it's more important to show that you can follow this step. It's a methodology that you can follow to get valuable information. And because of this, we changed for methodology, because this methodology can be followed for different purpose, and you can use specific steps, or you can not use just one step because it's not interest for your context. Because of this, we change it for methodology. Reading and understanding this contribution or this goal to use in different for different purpose.
Right, but sorry for being insisting in this topic, but at least I wouldn't put output input in this figure. If you are proposing a methodology, I would put the sequence of steps, not necessarily with input or output. In particular, because you don't use every steps, and also when you put output in the input, somehow it reminds me a process or a workflow. So I think that it would help you on this definition. I'm not sure. Actually, I'm not sure about that. I'm really not convinced yet if this is a methodology as it defined. I understand that you are trying to provide a sequence of steps to guide everyone that try to deal with data from IoT, but I think that you should discuss or think more about it, about this definition, right? Another point related to the methodology and also data instrumentation, you use the only SACR, the reference. And then I went through this reference. This is not so relevant work, at least in number of citations. And then I asked myself if there isn't another reference that you could use here to help you on these definitions.
Yeah, I use it SACR because as I answered Professor Annelies, my goal with this reference was to show that it's important to analyze the data and get valuable insights. And this reference SACR showed this. The SACR work presented how the network data can assist different solutions for smart healthcare, for smart city, and many others. So my goal using this reference was to improve the importance of the Flipper methodology. But I did not use a lot of reference to explain the Flipper methodology, like the steps, because I use it in Motif, IoT Required, in other, so I did not use so much in Flipper, because when I created Flipper, I already have read this reference and I already know, so I did not use it in the Flipper. Maybe I can add more reference, but I use it a lot, the SACR, because I want to show the importance to create the methodology. This was the goal, to use this reference.
All right. It's still related to Flipper. I have one question here. What make it different from other steps used for data analysis? Because you mentioned in one of your slides here, I think that it was 18, that the methodology, the sequence steps, was designed for IoT applications. Mm-hmm. I think that you make this statement. Yeah, and then what makes it different from other data analysis? Because somehow I got familiar with these steps. Mm-hmm. Let me just contextualize you. One of my PhD students that has just finished his PhD, he works exactly the same steps that we are showing here. Mm-hmm. We did exactly the same. What makes it different from other applications instead of IoT? What makes it different to apply in other contexts?
The most difference from this methodology, we have generic steps, because I also say this, that we can use generic steps from other contexts to apply in here. But the main difference is here in discover the most relevant features, because what I found in the literature, the works, they can use the feature selection or extraction feature to reduce the dimensionality, but it's very difficult that the works use this point, this step, to understand the data and understand the features relevance. And I want to give this insight through through the Flipper methodology, that you can follow the feature type context, the cleaning, the extraction, the missing data. It's very generic from other steps that I use it from this generic step from machine learning, from big data analysis. But I want to show a different point of view. We can use PCA, FEA, or other analysis techniques to reduce the features used in the analysis, but without analyzing, just running and picking some result and we're going to apply the machine learning. But here I want to do more. I want to analyze this feature, discuss the features, use these features to understand the behavior of the devices. So this is the difference, that you can follow a generic sequential of steps, but we can use this from a different point of view. And this
in this case, sorry for the interruption, but in this case, don't you think that you should highlight this step here, and then bring a discussion about this step specifically? Because this is the part that is different from other data analysis steps. So
maybe I can do this discussion specific. I try to do in the IoT regard because it's where I use it to discover the most relevant features. So I made a big discussion in there with a lot of results and discussion this. But when I showed the flipper, I thought, okay, we can follow this methodology for different reasons. So it follows generic steps, but at the same time, we are showing a different way to use. This is because I did not specify the relevance feature, because I did this in IoT regard. So my point in Flipper was to bring a methodology that I can use for different contexts in IoT. This is because I did not mention it a lot of the discovering relevant features. Maybe I can increase a little bit the discussion, but this is because I did not do.
Right. Okay. Still related to Flipper. If I asked you about a core contribution of this work, of your thesis, a core contribution, which one you would choose? Because there are many contributions, right? But which one you would say, this is the one contribution of your thesis?
The main contribution, I will not pick a proposal specific. I think the main contribution of my thesis is to use the network data instrumentation and feature exploration as support for other actions. But
this is the title. This is the title of your thesis, right? No, that is not the title. Right, sorry. Okay, go ahead.
It was my hypothesis. So IoT network data instrumentation and support for network management in security and performance. So throughout the thesis, I showed this, how to use the network data instrumentation as support for other actions. So I use it in Motif, I use it the previous knowledge in Primus, and I use in the IoT regard. So from my point of view, this is the main contribution, the network data instrumentation to analyze the data, get valuable information, and use this to perform some action in the network.
Let me make my question another way. What is the core problem? What's the problem? The problem of your thesis? The main problem
of my thesis. I have this in a slide. Let me. Oh, it's not changing with the numbers. Weird. Let me go. I have this slide. But my problem here. My main problem has threefold concerns. So I used all of this information to explain the main problem, but the main problem is related to performance, security, and privacy for smart application from IoT. So the main problem have three main folds regarding the performance. So how to achieve the requirements of critical applications, but at the same time that we are in a smart home, we can have attacks, because in Motif I identify the traffic of this attack, the devices, the traffic of the devices and applications. So this also can be used by an attacker. So the problem is regarding the performance of these smart applications and the security when attacker can infer the user activity. And this kind of attack violates user privacy. So one is connected to the other, but the three main problems are performance, privacy, and security.
I would say that this is the application, the relation of the applications of your solution, but not exactly your problem. You should. One of my notes here is you need a better problem formulation. Okay. If I asked you to put present here a problem in one phrase, that's what I'm expecting of you. But you don't need to do that right now. But I know that the solution is related to performance, to security, to privacy. But let me explain to you why I'm asking these two questions, these two last questions. Because I think that Flipper is the main contribution of this work. And then actually Motif, IoT Guard, and then Primus is actually application. I'm not sure if it's a use case, but it's the application, it's a way of validation of the methodology. I totally agree, I totally disagree when you say that the relation of this product of your thesis are out of the relation of them are out of the scope of your thesis, as Annalise has asked to you. Okay. I totally disagree because I think that you are presenting different application of your methodology. That's the way that I see your thesis, and then Flipper is your main contribution.
Then, just sorry for interrupting you, but Andressa has a slide where she presents the problem very well, and this one is not exactly the one. Andressa, you have one slide here that shows the problem that you are achieving or addressing in the thesis, and it's not exactly this one. It's that one that you mentioned that the data that we have is unbalanced and etc. So this is the problem. This
is the problem, right? Yeah. Right.
Yeah. So now I pass the ball for you, Andressa. I just
but I agree, but when we say that the Flipper is the main contribution, yeah, we can say that because Flipper performed the network data instrumentation. And I try to say this, but without mentioning Flipper. So yeah, the main contribution is the methodology that we follow to have a network data instrumentation and feature explorator to get valuable insights. And I use this in all my methods and architecture. I agree with this, and I try to say this, because the network data instrumentation and feature exploration is the gold in here, we can say.
But Andressa, he wants to know the problem.
The problem is because when we look to the IoT data, we have unstructured data, we have noisy data, missing data, and how to achieve, get valuable information from this messy and unstructured and uncorrelated data. How we can achieve smart data-driven decision if when we look to the IoT data captured from the network traffic is messy. So how to structure this data, how to organize this data.
Okay. And then still related to the problem definition, I really miss here a list of challenges. Okay. You should list here challenges to make it clear the challenge that you have to address this problem. So you need to provide to the reader the importance of your work. And then when you put a list of challenges related to the problem, you convince better the reader what are you are trying to solve and the challenges associated with it.
Yeah, I think I try to do this, but without success. So because I try to explain the missing data, the noise in data from IoT, the huge amount of data, but maybe I can discuss a little bit about this. So yeah, okay.
And then also you're gonna be scared because this is my general comment, it's still my general comments, but it's still related to my general comments. I also was a little bit concerned about the amount of topics that you are involved with this thesis.
Okay.
I know that when you are involved in a PhD research, you do a lot of things, but you don't necessarily need to put everything on the thesis. So you are involved with so many topics that sometimes you should be careful with some statements. So I will show you, at least in the text that I will send to you, right? Some I will provide here. Okay. So let's go through the section 1 here. Page. Okay. Right. That's the point. Page 19.
Okay. The goals.
Yeah. Page 19. This paragraph here, this paragraph. When I was reading your thesis, I missed a methodology of the thesis as a whole, in general. The thesis, what methodology you use for your research in general. And then I noticed that your methodology is right here in this paragraph. So maybe a good strategy is to say what was the strategy that you adopt to validate your thesis. Actually, you develop the Motif method. You develop you design the architecture, and then you also design the IoT guard, IoT guard. Let me see here the name.
Yeah.
IoT guard. Exactly. Yeah, exactly. So I think that this is the methodology that you have adopted in your thesis in general. So I would create a subsection here to provide this information. Let's see here. On chapter 2, right?
Okay.
I would be happier if you use in chapter 2 a background, but related to the problem, unstructured data.
Okay. Okay. Yeah.
Because as I was saying, you have studied or you have been involved with so many topics in IT in general. So then you put everything in this section. But the most important part of your thesis is that data instrumentation, data analysis, how you structure data. And then I missed it here in this chapter. So I would be happier to see some sections. For example, you mentioned about IoT in general, but section 2.1 is enough. IoT application diversity and as health requirements. You don't need to explain what is IoT and then contextualize IoT in general. I don't think that's the case. But the most part here is section, just a moment, is section that you mentioned about data instrumentation. I think it was data
instrumentation. It's, let me find.
Yeah, section 2.2.2. Yes, this one. So when I saw this chapter, I went directly to this section to see what you would say. And then it was just a few paragraphs, 2 paragraphs. And then that's why I think that you should explore more this subject on this chapter. And then you provide some discussion about network slicing. This is a topic that I'm very familiar with. I'm not sure, because you have used on your Primus architecture, network slicing. So I don't think that you need to provide this discussion here, because there are some, let's see here. No, it's not in this chapter, because there are some statement that you provide here that is very questionable. Let's see. It's not this in this chapter. I will show you. Okay. Let's go to chapter 3.
Maybe it's in the Primus chapter. I don't know. We are talking about network slicing.
I will show you. It's later. It's not here. So one point that I really like to have some explanation, because not my field of research. Okay. What is the difference from e-health, s-health? S-health, I know that is for smart health application.
Yeah.
But in your thesis, what's the difference between them?
I use it sometimes as similar, but when I look and dig in the literature, they use a lot the e-health for explaining that there is health related to technology. So is all the kind of technology related to the health, or to improve the health, or to be used for something in the health of users and patients. But when we are talking about smart, that is the S-health, I am focusing in the smart healthcare, the scenario definition of IoT and the smart applications. So we can, I have a look from the literature, then e-health is here, but smart healthcare is more specific for a context, because e-health is technology like mobile, involve other things. I think Professor Burak want to say something.
Yeah, just a quick comment about it. E-health is more service-oriented, actually, if I may jump in. Whereas smart health is more methodology and technology solution-oriented. So just to wrap up what you've been saying.
Okay. Thank you, Professor.
Sorry.
Right. Thank you, Professor. All right. Okay. So let's go to chapter. Do some. Some question I have already made here in my notes. Some others Annalise has already made.
Okay.
Okay, could you please go to slide 27?
Just a moment. Can you repeat the number, please?
27. 27.
Yeah. Here, about the motif, right?
Right. Can you go to the other one? I think that
the
it
other
was.
one is the publication.
No. Go.
Then
Previous one.
Maybe the previous
27. Right.
27.
Because yeah, 27. The next one. Yeah, this one.
Okay.
Okay. Could you please tell me what is the contribution of a flipper to this result that you have presented here?
Oh yeah. The flipper, I used some steps from the flipper as support to implement on Motif. So as I say, the flipper support the Motif and other methods and architecture. And here from flipper, I use the pre-processing, the cleaning, they're removing unnecessary data, and I also use a distraction. But here in Motif, I did not use the discovering of most relevant features. So I used a set of steps of Flipper, but other ones I did not use. And then I used this step because the goal was to identify the traffic of each application from the smart home.
But do you think that the use of Flipper has contributed to these results that you are claiming here?
The steps,
or the steps that you use from Flipper, do you think that they have influence on the result that you are presenting here?
of course, yeah, because the steps are the most important process of the Motif method, because if we do not extract features from the network traffic, or if we do not deal with, for instance, if we do not deal with missing values, we will get error in the machine learning algorithm. So the steps from Flipper that we used in Motif, they are very important to achieve a good result in the traffic identification. So yes, they are very important, and they make difference because analyzing the features and extracting the statistics from the features, increasing the samples, it also improved the machine learning results. So yes, this important, these steps that we use it in and instantiate from Flipper, they are very important. And they made Motif because we create a steps of the Motif to perform this goal, to achieve this goal.
Okay. Okay, let's go to chapter 4, Primus.
Okay.
Here. Remember that I said to you that there are some statement that is questionable.
Yeah,
and on table 4.1, for example.
4.1. Let me go to there. Just a moment. I am in overleaf, so it's more. Okay.
Okay.
Related words.
Yeah, but the table, for example, the table.
Oh, yeah.
These work are really the main works of network performance management?
Sorry, I didn't understand.
The work that you are mentioning here, they are really the main works of network performance management?
They are not just related to network slicing. I try to show a biggest view. Maybe this is not clear in the manuscript. I try to show this in the presentation because first I researched in the literature about resource allocation and quality of service techniques that try to achieve this quality of service. So I researched about resource allocation, traffic shaping, traffic separation, and scheduling without network slicing. I made this research first, and then after this, I started to research about network slicing. Then I realized that the works, they mix it, the approaches, like we did in Primus. For instance, in Primus, we used network slicing with priority, so a priority queue. So we mix it two approaches.
But my question is, you are saying that these are the main works of network performance management.
Oh, the title of the table. Now I see what we're talking about. Main works.
Including your works, yours.
This work 9 is for my master degree, but I call it the main works related to the approaches and related to the requirements and implementation that I considered. So they are the main works regarding this information. So looking to this information, like the approach considered and the requirement, okay, they can be the main works, talking about these approaches used to achieve some requirements. In this point of view, yes. But if we look to the main works in network management, performance management in general, not looking these requirements that I mentioned, then no. But I try to specify these points in my table. Maybe I can do this in the title also to be more specific.
Not only the title, also in the paragraph. I
call it the related work on network performance management. It's because I was trying to show that I was talking about works that try to improve the performance in a way. And then I start to funnel, to tailor for some approaches. Yeah, maybe I can review this, but the goal that I use this information, it's because we have two lines. Yeah, we have the network performance management and the security in the other chapter. So I try to show these two differences. And this is because I use this term. I don't know.
Okay, another example. Go to page 81.
Okay, it's the next one. Here, which
another example, just another example. You said network monitoring on this paragraph. Yeah, network monitoring, employees, traffic separation. So this is the kind of statement that is not effectively true. It's not always. So I think that you should think more about this statement, because as I was saying, you have involved with so many technologies, so many concepts, that is easier to make some mistakes. That's why I'm saying this to you. So I would adopt another strategy.
Okay, I see.
Okay,
I understand.
But there are others. There are others that I have highlighted here on the text.
Okay, great.
So let's see here. Okay, on section 4.2.1, I think Annelise has already mentioned something about network model.
Yes, she questioned me about the overview of the model. I think it's
but my comment is another one. That's why I'm still.
Yeah, go ahead.
4.2.1, section 4.2.1, network model. On the text.
Yeah, here.
Here, yeah. The formulation that you are providing here, could you go to the other paragraph, please? Yeah.
Okay.
This is the type of formulation that I could not understand. What do you mean by give an application app, where app is the group, 1, 2 app, the application? So this is the type of formalization that I couldn't understand.
It's missing an N, right? I want to say that is a set of application, but it's missing the N because I want to show that is an infinite number of applications. We have a mistake in here. Yeah.
Mm-hmm. And then also, when you say a set of available resources, network resources, 1 to R, I don't know exactly what is R here.
Yeah, it's the same thing for app. Yeah, it's because I want to show that we can have a set of resources available, a set of different applications, but we don't have the exactly number of resources and applications, but it's missing the N, like the set of requirements, key N. So it's missing this ladder in application and research to represent better this information.
Another point, could you please go forward to the other page? Yeah, this one. And then you mentioned about the slices, the number 8.
No, I repeat this in a lot of, yeah.
You mentioned about the number 8 slices, even in your presentation.
Yeah.
Where did you find this number?
In these two reference, they define.
Because you said that the number of slices is 8. Cannot be greater than 8. And then I got surprised.
I agree with you, but I did not make up this information. I picked from I use it from the literature, because reading about network slicing and the 3GPP, they really defined this number. So I use this number based on what they say. So I use this reference.
Okay, but actually we can use a bigger number of slices.
Okay.
So that's why at least an explanation about this limitation for 8 slices. Okay. Even in our presentation, you mentioned about that. Okay, let's see here. There are some comments here that I decided to not make here. You can see it later.
Okay, this is great. And I can...
Onus, the controller, onus. You implemented onus? You use the onus controller?
Yeah, we used the onus as the controllers, because they were indicated to create the tenants. So we decided to use onus, and we use it as hypervisor, the OpenVirtex, Libera from OpenVirtex.
But you use onus in which environment? You mentioned Mininet Wi-Fi?
Yeah, we use
Okay, go ahead.
Yeah. We used the Mininet because we wanted to implement virtualization. So yeah, we need environment that allow this. So we decided the Mininet. But we are talking about the focus is smart application, is IoT. But then we found the Mininet Wi-Fi that is available on the GitHub. We have we have available in the internet. So we decided to test the Mininet Wi-Fi, and we used the Mininet Wi-Fi to implement the scenario. It's a small scenario, as I said to Professor Annelies, but we created on Mininet. And to create the environment, we used the hypervisors and the controllers. We decided to use these tools because when we are looking and researched about network slicing, we found we are looking to some virtualization that was using the tenants and these concepts from network slicing. We tried to use the most related tool from network slicing, but this was very difficult because there are a lot of words talking about network slicing, but when we talk about virtualization, there are several different tools also, but we use the ones that they mentioned, the tenants, and to create several tenants for the applications and to create the dynamic environment. And this is because we decided to use the Libera, OpenVirtex, and the onus as the controller.
What drew my attention here, it was because you use Mininet Wi-Fi in conjunction with onus. And then from the technical aspect.
Okay.
And then I was curious about how you put everything together. Because I know Mininet Wi-Fi. I have interacted with people from Unicamp that had developed Mininet Wi-Fi. And then that's why I asked about onus. Onus in conjunction with, coupled with Mininet Wi-Fi, they together.
Onus is open source.
No, I know, but
so
but couldn't find the one environment to use they together.
Yeah,
Mininet Wi-Fi in onus.
We installed onus on Mininet Wi-Fi. They have the documentation, so we follow this documentation to install it. It was a little bit difficult because we take time to do this. We did this in me and my two colleagues together to implement this environment. So we took a long time to implement. And these tools, they are a little bit difficult to use.
That's why I'm asking you.
Yeah. So we decided why we used the ONUs because they proposed the SDN and NFV solutions. So we followed the documentation and installed it in Mininet Wi-Fi. Following the documentation, we were able to install and use as controller.
Okay. So let's go to chapter 6 to finish my comments. There is one question here about IoT. How do you IoT regard?
IoT regard.
Yeah. The motivation for use this tool is that, let me see if I'm correct.
Okay.
The motivation is that if the AP is compromised, right? If the AP is compromised, you can see the traffic. Is that so? What is the motivation to use? Because there is one figure. It's like 4.7. Can you go there?
Yeah. 4.7.
Because we mentioned about you make some assumptions.
Okay. Go ahead.
Right.
I'm with the slide in here.
Because I missed a threat model on this problem here, but this is not the case. My question is, you have mentioned about the motivation to use IoT regard.
Okay.
Which can you explain? Can you say again? What is the motivation to use this tool here?
Oh yeah, I can say. It's because, okay, let's start with the point that we can get valuable information from the network traffic, network data instrumentation. So we can perform network data instrumentation and feature exploration. And this network data instrumentation and feature exploration assist the network performance management. But when we finish this work, we start to look into this network data instrumentation from the adversary perspective. But at the same time that we can use this network data instrumentation to assist the network management for good reasons, someone also can perform these steps for a bad reason, so to perform an attack. And the traffic side channel attacks, traffic-based attacks, they are very known in the literature, and they perform some steps similar. They collect the data from the wireless, medium wireless, and they collect this data, collect the network traffic, extract features, apply some statistics to infer the user activity that I try to show in, I have one slide in here.
Yeah. This figure is exactly.
What I try to show is that we can use this for a good reason. Okay, I need to increase the bandwidth or increase the resource, but also someone can use this to understand the user activity inside his home. And I try to show this through the IoT regard. So the motivation was, I can use the network data exploration to understand the user activity. And I use it, I did this in the IoT regard, and I say, okay, let's try to improve the obfuscation or the defense. And to do this, we masking the network traffic through approaches. So, but answering your question, the motivation was to show that at the same time that someone can use the network data instrumentation for a good purpose, for network performance management, someone can use for an adversary to perform an attack. Can
you go to the next slide, please?
Yes, sure.
So the other one. One more.
Yeah, this one, right?
No. So
let me put here, that is easy. The feature exploration.
This is the one that shows the bad guy. The one that shows the bad guy. Yeah, this one. So in this scenario here, this sniffer, the bad guy, is in which place here in this network scenario?
We consider a scenario that he's close to the smart home because he needs to collect the traffic. So he needs to capture the traffic from the Wi-Fi. I try to show this in the figure through this red line, but maybe I can.
But he is located on AP?
He's close to the smart home or in the near to the smart home to be able to capture the traffic from the wireless network. So
but I'm assuming that this place is the AP because the
Okay.
the only place here.
Can be. I suggest this position. Yeah.
Not only the attacker can be authenticated in the AP and then can eavesdrop the Wi-Fi communication there.
Can be inside the network.
Yes.
Yes. Okay, because I was assuming, I'm not sure if it is right on the text or it was my impression, because IoT regard is installed in AP also. That's why, that's the reason for my question.
I see. It's because in the text I suggest this position.
As
the position to put the IoT regard, to collect the traffic, reveal, and then mask. I suggest this in the text.
Okay.
This is because probably. Yeah.
I'm almost finished. Let's see here. Let's see. I also agree with some question of the analysis that I was about to make. I missed some example of feature extraction, that feature selection that you use in your data set, in your experiments. I think that you should put here some example, at least as a attached to your thesis, because somehow I missed some technical aspects of the implementation that you have made. Right. Then I agree with the comments of Annalise in this regard. So I think that's it. Let's see here. Okay. Chapter 6, the conclusion.
Let me go to there.
You on page 142. 142.
Sorry. Let me
142.
To open the.
Yeah, because the PDF is heavy.
Yeah, here I have the. Whoops.
One.
Here. 6, chapter 6, which section? 2.
Yeah, because you okay. One before previous one.
Contribution.
Yeah.
142.
The other one.
Oh,
that's
okay.
Stop.
Sorry.
You decided to use network traffic analysis, not that instrumentation.
Yeah, you're right.
Is there any reason for that?
No, you're right. And all sentence, okay.
All sentence. You decided to use network traffic analysis. That made me confused. Then
there is no reason I supposed to use network data instrumentation.
Okay.
Yeah.
And finally, is about your publication list.
Okay.
There are some work really related to Primus that is not directly related, and then you are not the first author.
Yeah.
Is there any reason for that?
It's because we work together. So I am not the main author because it's the work from a master degree from my colleague. So they are the first author, but I assist in the research, in the evaluation. So I am also part of the work in the contribution, in the publications. That is because. And the IoT Reward, he was created based on the work that we made with the master degree from Nelson. So we have this research, start to look into this point, and then we improve it, and I improve it in the thesis also. This is because we work together.
Okay, Michelle.
Thank you.
That's all.
Thank you so much, Leovino. It was very good, your comments, and few steps that we just missed, and that's and we could not correlate.
Yeah, all the comments is on the text on PDF. I will send it to you. Okay.
Thank you so much.
In order to not take so many time for take so long for my comments. So I will send to you.
Thank you so much, Leovino. It was very great, and I think it will contribute to finish very well the manuscript. Okay, so now we go to Professor Wagner. Wagner Zola is internal member from our program. Wagner, thank you so much.
Hello, can you hear me?
Yes, and see you.
Can you see me too?
Yes.
Yeah.
Okay. So I'd like to thank Andressa, Professor Michel, and Professor Burak for inviting me to this thesis committee. I think that the work is very complete and very well done. You had very good results. So I have to congratulate Andressa and both the advisors for this work. First of all, I have some questions. I couldn't pass this first opportunity to ask. Some of the results that you showed you have collected elapsed times on some methods and or architectures. Some showed elapsed times around hundreds of seconds. So my question is, I know it is not your research area, or but sometimes you already have considerable overhead in the system, like virtualization stuff or some others. Do your methods benefit or require high performance processing or accelerate computing to be effective, for example, in methods or put in line something? Do your methods require some kind of acceleration or high performance to be put in line with the traffic analysis, or will it be always offline or something like that?
I see your question. If we can analyze online and do this network, I discussed this in the limitations and the discussion in the final of IoT Reward, I think, and Motif, because the goal in a realistic scenario is important to analyze online. So we can analyze, collect a small amount of data, so we cannot analyze a huge amount of data, collect this data, analyze, and create adaptive solution or do something online. So yeah, this can be a good option of implementation, but as we did not know in the first, in the beginning, how it works and how it performs, we decide to do the analysis all offline. based on a data set with IoT, but I suggest as a future work or other things to analyze in streaming or online, maybe considering concept drift or something like that, to analyze the network traffic analysis, network data instrumentation in an online environment. But we did not focusing in this thesis because, as I said, first we were trying to analyze this test, have some results to understand how it performs and how it works. Maybe can be a second step for a future work or for someone continues the work. I don't know if I answer you.
Yeah, okay. Thank you. Second, in like, I think the term structured data or structuring the data, as you emphasized in the beginning, it confused me a little bit, somewhat, because in a sense, the network layers and packets, they have some structure, and they have an, like, even the payload part. If you look at the payload, they have some structure for each of their own applications, right? And some applications are emerging every day. So maybe, I don't know, maybe the concept could be knowledge acquisition or acquiring relationships or acquiring features or classifying standardizations on views or on the structure. Because, for example, to this point, I think this whole Babel Tower of different applications, right? So to this, I think the slide 9, as Michelle pointed before, better points this point, like you say, unstructured, uncorrelated, and unorganized, and you have concentrated on structure in the beginning, and then it made me a little bit confused. I think, as I pointed, the term only structure, they have some structure on their own. That's what I think, but they're not correlated or organized, and you don't know how to relate them, how to correlate them. Is that correct?
I see. I understand your question, and why I decided to use the term structuring network data instrumentation. Sorry, it's because we part from the beginning that when we look to the data, is an unorganized data. So if we consider the raw IoT data, we don't how to achieve a get a valuable insight from the raw data. So it's necessary a pre-processing to achieve the insights, the valuable information, and to make some acquisition knowledge. So to have this acquisition knowledge, it's important to pre-process this data. And this pre-processing, all these steps from Flipper, right? I call it as a network data instrumentation, because I am treating the data, dealing with them to be possible to have a smart data-driven decision and get valuable insights. This is because I use this term, and the traffic classification, for instance, to classify some traffic is necessary some organization, some previous work in the data to be possible to apply in machine learning models. So even for that, it's necessary some instrumentation. So this is because I use this term. Maybe I can clarify.
My thing is, like, when you think about human texts, like your thesis or some book, right? They have some structure, although we can say it is unstructured data, because every book or every text will follow some subject or some structure, different structure, like, and that's why the term unstructured applies. But if you see like a data structure, you see the structure is fixed, and to this extent, I think networking network data, even coming from devices, they have some structure, their own structure.
Yeah, I understand.
That's why I'm confused by the term unstructured per se.
Oh, I made this discussion on the manuscript about the PCAP file. So we have a network capture a network capture. So we have this PCAP file that has a kind of format, right? We have a format in a PCAP. We have the IP, we have the sequential of the packets and many other information from the network layer, from the layers. So we have a kind of format. I understand what you want to say. And this is because in the instrumentation, they defined structure, unstructured, and structured. So the goal is to achieve the structured data. And here, what is a structured data? We have a table with columns, and we have the features with the values, the most relevant features. This is the goal, to achieve this kind of format. And when we look to the PCAP, for instance, when we collect the data from the network traffic, we are looking for device data, data collected from the device that have some kind of format. But even though, besides have this format, still we cannot get some valuable information to apply in network solutions for smart data-driven decisions. So if we preprocess better this data, take more, analyze more deeply, and get the most relevant information, make these steps, we can achieve a most structured data from the raw data. This is the goal of these steps and the instrumentation. We have the input raw data without has a prior format, but it's not a format that can give to us valuable insights. And this is the motivation to create these steps and achieve some insight. Professor Michelle, do you want to say something? Your hand.
Yeah, Andres, I think if you go to the concept of this unstructured data, machine learning concept or area, I think could be easier to Professor Wagner understand what you mean, or what they mean by unstructured data there, and the difference between what he's saying about structure. Because here we have really, we have an intersection between areas. And of course, this can be very confusing. And I thank Professor Wagner for bringing up this point, because it's something that should really be very clear in your manuscript. Like, if you explain what is unstructured in the sense that you are seeing your work, like when you collect all IoT, the data from IoT, why that data is not structured? And this is the question that he's making here, I think.
Yeah, thank you, Professor.
Yeah,
I can clarify. Yes,
maybe this is related to subjects that people on databases work, like knowledge representation, or analyzing many other formats in many databases, many stuff like that. Perhaps and they are also applying AI methods. So maybe there is an intersection here that would be worth verifying. But I just wanted to make this point. So back to my annotations here, let me see. I have a very few annotations in the manuscript, and I'll be sending to you afterwards. Very few. I think the work is very well written, I have two brief comments to begin with. I have just very much like the chapter 2, but I feel like sessions like section 2.2.3 is feature extraction on network traffic. I think it deserves like another table, or maybe a flow chart, as you did in the other chapters, summarizing this section here. Perhaps some others in this section too, or maybe this is related to what Annelise observed, as she wanted to bring stuffs from the other sections to this section too. So perhaps that's why that's the same, some other aspect of the thing. So the second, let me see here. This is important. In the abstract, I felt that the abstract deserves the addition of extra statements about the novelty or the contributions, because I see this in the introduction, I see this in the work per se, but I think the abstract did not convince me so much. So I think you have to pay attention and take a moment to make some additions to the abstract to this point. Okay.
Okay.
Let me see what else I have here. So I'll be sending you all my annotations. And again, I won't take you any longer. I think I'd like to thank again the advisors and Andressa for the invitation, and congratulate you all for the great work. Thank you.
Thank you, Professor. Thank you.
Thank you, Professor Wagner. Now I open the floor for Professor Burek, if you want to say a few words or question. Andressa.
Well, we've asked all the questions actually throughout this process, so I don't think I will ask too many major questions, but still I would like to revisit one of the questions that was asked by Professor Leobino. So the question was about the core contribution of the thesis. So I'm going to ask it in actually a different way, because the contributions of your thesis is actually twofold, and one of them is actually from the standpoint of network operations and management, where you have three main contributions to make that plane robust. And the second fold here is the security aspect against traffic-based attacks, where you have this IoT regard solution, as you have already presented. But overall, there are 4 pieces here that adds up into these 2 folds in the thesis. Now, my question is that what is your favorite, in other words, contribution in this thesis? I know you don't want to pick one, but you should pick one. You know, even parents actually have a favorite child, and children have favorite parents, right? So you should pick one.
I think I can answer this related to something that I say to Professor Michel last week. It's because the learned lessons came from network data instrumentation. So in the PhD, I understand that it's very important to analyze data to get valuable insights. But it's also, now in other perspective, is also important to analyze how we growing up over the years, so how we improved our work. So looking to my thesis last week and this week, I saw that the IoT regard is the most complete and most discussed method. So I discussed it a lot. I presented a lot of results. I have a lot of discussion on the proposal, the related work. So I think it's a very complete work. So I think the IoT regard has a good contribution and it is a good work, but it also flipper because we have a set of steps. So I think the two of them, yeah.
Okay, and I have a second question. As I said, I won't ask major questions because we've discussed all the details throughout this process, but these are just to understand your vision. That's why I'm asking. The second question is, let's assume we want you to start over the PhD and do this thesis from scratch, and we just give you carte blanche so that you can do anything. You want any additions on top of this, you can maintain the work as is. Now, what would you change in your assumptions, in your settings? I'm assuming you would want to keep and maintain the core of this thesis as is, but we're going to give you that flexibility to redo everything and bring a new thesis. Now, what would you change in terms of your assumptions, in your analysis, in your simulations, and in your settings, experimental settings in general?
Okay, this is a good question. I like the way the thesis are now, so is now. So the main core contribution, I like this. So I like network traffic analysis and what I work it. So I did not change this, but I like it a lot to work in the smart healthcare field. And in the IoT regard, I did not focus in the smart healthcare. So maybe I changed this. I don't know, adding or performing some analysis specific of the attack in the smart healthcare, because we don't found much in the smart healthcare. And I think this is a very important and critical scenario for the future network. So maybe I change this, adding more the smart healthcare in the IoT regard. So then I think all the theses will be focusing on the smart healthcare and not smart home and smart healthcare. Maybe this topic.
Well, great answer. Thank you very much, Andressa. This is a very solid work, in my opinion, and I really enjoyed also working with you and Michelle. And I thank you very much for the hard work and dedication. Of course, there are a few issues that need to be taken care. We've been discussing since the beginning of the defense that's the whole purpose. But overall, I sincerely thank you a lot.
Me too. Thank you very much for all the support, Professor. It was a great pleasure.
Likewise.
Thank you so much. So following the rules of our program, now we go to the third step of this defense. I will invite Professor Annelies, Leobino, Professor Wagner, and Burak to our breakout room. I will create here and I will put you all. So Andressa, please just wait here. We come back in a few minutes.
Okay, that's okay.
Will I be transferred automatically?
Yes.
Okay.
You need to accept, of course.
Okay.
That's great.
Hello.
To record. Okay, Andressa, so the jury committee members discussed it. Of course, we have you know you have things that can be improved in your manuscript, and I'm sure you will do in these next days. But all the members was in favor to approve your thesis. So congratulations.
Thank you. Thank you, everyone. Thank you, Professor Michel, for the advisor, the support for all this year. The teachment is very important. Thank you for my co-advisor, Professor Burak, for all the support. It was very important too. And thank you for the committee members, for the commentaries. It was everything very important too. And I take it notes. I will analyze them, and also thank you my co-authors, my colleagues, for everyone from the lab. Everyone helped me, so it's very important. And again, thank you, Professor Michel, for everything.
Very good. So thank you too also for all the effort, and for sure you will be recognized along, you have been recognized along this path from your efforts.
Yeah. Thank you.
Congratulations, Andressa.
Thank you.
And Professor Burak. Congratulations. Very well done.
Right. So, have some rest from now on.
Yes.
Yeah.
Congratulations, Andressa.
Thank you so much.
Thank you so much, every one of you, and all the audience that supported you until now. So I declare this section closed. Another thing that I just didn't mention, Leobino and Annelise and Wagner, you will receive email from our administration, and they will send you an electronic document to sign with the approved mentioning in these documents. So you receive from PPGInf, PPG and INF from UFPR. Thank you so much again.
Okay,
Thank you,
bye-bye.
everyone.
Bye.
Bye. Thank
Pleasure
you.
to meet you all.
Bye.
Bye.
Bye, everyone.
Bye.
Congrats again, Andressa.
Thank you, Professor.